So we just saw an example where Green's theorem was not so much fun to use, but this example, Green's theorem, will be easy to use. And we're going to use it because these are all closed paths. This is the unit circle on 3 different vector fields, and we're going to find the flux for all of these. Now, it's okay to use Green's theorem because these are closed circuits, but I also want you to remind you that we've already done these exact same circles on these exact same vector fields, but back a couple examples ago, we found circulation. So we used Green's theorem, but we used the circulation form. So now we're going to use Green's theorem again, but we're going to use the flux form. Okay, so let's begin with letter A right here. So the flux, according to Green's theorem, would be equal to the double integral over the region of f sub x plus g sub y dA. All right, so what is f sub x? So f sub x would be, so remember this is our f now for this particular problem, and this is our g. Okay, so f would be x, so the derivative of f with respect to x would be 1. So that's 1 plus 1. Now, this is a circle, and when you have to integrate a circle, generally, polar is easier if you can manage it. And we can. So what we're going to do is we're going to multiply this by r dr d theta. R is going from 0 to 1. Theta is going from 0 to 2 pi. And we're using polar because polar is easier for a circular region. There, I just wrote that up a little bit. It's easier for a circular region. And then I should shade the region. The region is actually the interior portion because it's two-dimensional, right? Not just the circuit around. Okay, so we're going to integrate r with respect to r. So that's just, 2r with respect to r. So that's just r squared. And the 2 pi can just come out because there's no theta in any of this. So what we're really doing is integrating 2r with respect to r from 0 to 1. That would be 2 pi times r squared from 0 to 1, which is 2 pi. And if you look at it, you can see, right, there's a lot of flux on this particular problem, right? There's a lot of flux because the arrows, the vector arrows, are all pointing outward. They're pointing across the boundary. So the flux is positive because the vectors are pointing across the curve and outside the curve. Which, by the way, is the exact opposite of the circulation. This same particular problem had 0 circulation because it wasn't helping at all, but it has lots of flux, right? The arrows are permeating the barrier of that curve and going from inside to outside. Okay, now what about the rotational vector field? All right, so in this case, flux would be equal to the double integral fx plus gy dA. I'm just writing Green's theorem again. Okay, so that would be the double integral of fx is 0 and gy is 0. And the integral of 0 over a region is 0. Which makes sense. I mean, look at it. Those arrows are all going with the curve. They're not crossing the boundaries of that curve. So the flux is 0 because all the vectors are flowing with the curve. So there's a lot of circulation. There's no flux. Right? So these two are exact opposites of each other. If you look at the old one, when we did circulation, circulation on the first one was 0. So it has no circulation, lots of flux. The second one had lots of circulation, but no flux. Right? Nothing is crossing those barriers. Those arrows are all flowing with the curve. All right, what about the third case? Well, let's see what happens. So in this linear vertical vector field, so they're all pointing vertically upward, the flux, again, is the double integral over r. We can use this form because we can use Green's theorem, and we can use the Green's theorem because this is a circuit, a closed path. Okay, so this is the double integral over the region R of fx would be 0 and gy would be 0 again. So it's 0. Which, by the way, if you'll notice for both of these, what this means is the divergence is 0. This part right here being 0 means that for both of these, the divergence of f is 0. So this is a source-free vector field. So f is source-free. And you can see it when you look at it. It has no source. It's not everything coming out from the center, unlike this one, where all the vectors are coming out from the center. So this is a source-free vector field, and so is this. The divergence of f is 0, so f is source-free. Now, why is it happening when you look at it over here? We want to think about permeating from the inside to the outside. So over here you can see, hey, we're permeating from inside outside, both the top, right? Over here on the left and over here on the right, the arrows are pointing from the inside to the outside. But down here at the bottom, the arrows are pointing from the outside to the inside. So it's like you have positive flux up here and you have negative flux down here, and then they cancel each other out. Very similar to what happened to us in the circulation problem, right? But in this case, it's the top. The top has all the arrows pointing out, so that's positive up there for flux and negative down here for flux, and then they end up canceling each other out.